Hi, Mrs. KJ here, going over lesson 4.08, Review More Aspects of Heat. Review concepts presented in the lessons of specific heat and writing thermochemical equations. Every substance has a unique storage capacity for thermal energy, which is known as its specific heat or specific heat capacity. Specific heat is used to calculate heat energy transfer, which is important in many chemical and physical processes. Goals for this lesson: demonstrate mastery of important knowledge in the lessons, specific heat, and writing thermochemical equations. So I am not going to download the study guide because it's review, but of course that's where you can go to find the answers to the problem sets which we will be doing together. Key concepts in specific heat. Substances have thermal energy. Specific heat capacity or specific heat is the amount of heat needed to raise 1 gram of a substance by 1 degree Celsius. Each substance has a unique specific heat. Specific heat, capital C, can be calculated by the equation capital C equals Q divided by M delta T. So in other words, we have C is our specific heat equals the heat divided by the mass and the change in temperature. Again, Q is thermal energy in joules, M is mass in grams, delta T is the change in temperature in degrees Celsius. Specific heat influences the time required for heating and cooling. Fluids with a high specific heat are used to transfer heat in cooling systems for cars and spacecraft. Remember, if it has a high specific heat, it takes a long time to heat up and a long time to cool off. Heat capacity depends on the substance. Heat capacity is the ability to store thermal energy, and it influences heating and cooling times. So what's the example of something with a high specific heat? That would be water. And what is something with a low specific heat? That would be metal, because it heats up and cools off very quickly. Key concepts in writing thermochemical equations. Thermochemical equations must be balanced. The states of all reactants and products are noted in parentheses. The change in enthalpy or enthalpy of reaction, delta H, is written at the right of the equation. Endothermic reactions have a positive delta H, while exothermic reactions have a negative delta H. Changes in state contribute to the delta H. In multi-step reactions, delta H values can be added. In a reverse reaction, the delta H of the reverse reaction has the same value as, but the opposite sign of, the forward reaction. If you multiply a chemical equation by some factor, like if we multiplied it by 3, then the delta H are also multiplied by that factor. Standard conditions are delta H with a superscript of 0, or in other words STP, 100 kilopascals, 0 degrees Celsius. Remember, delta H tells you the amount of heat that is taken in or given off. Thermochemical equations show reactants and products. Thermochemical equations can be endothermic, which is a positive delta H, meaning they're taking heat in. Thermochemical reactions can be exothermic with a negative delta H, meaning they are letting heat out. All right, and then we're going to go to our problems and solutions book, and we're going to do numbers 1 and 2 for 77 and 79. And then there is the quiz to take after this. There's some other websites if you want to check them out. They're on slide 7. You are more than welcome to. And let's go ahead and check out these problems. Okay, problem set 77, specific heat. The objective: perform calculations involving specific heat and heat transfer. The specific heat of a substance is a measure of the amount of heat necessary to raise the temperature of a sample of the substance. Specific heat, or C, also called specific heat capacity, is defined as the quantity of heat that is required to raise the temperature of 1 gram of a substance by 1 degree Celsius at a specific pressure. The specific heat of liquid is relatively high compared to that of many other substances. This high specific heat is one of the reasons that the Earth's climate is relatively moderate. Earth's oceans absorb and store a great deal of heat from the sun during the day. They release it slowly at night, keeping temperatures relatively stable. That's why if you go to other places at the same latitude as Minnesota, so if you go over to Europe at the same latitude, 45 degrees north approximately, you will find that some of them have much warmer climates. For example, in Great Britain or England, because they're surrounded by the ocean. So because they're surrounded by the ocean, they have all that extra water that has a high specific heat capacity, and that water helps keep the temperature stable because it takes so long for the oceans to heat up, so long for them to cool off, versus here in Minnesota, unless you're right next to Lake Superior. If you're in the rest of Minnesota, then you are going to be surrounded by land, which has a low specific heat. So it heats up quickly, cools off quickly. So it's kind of interesting how that plays a part in the weather, which we may not have thought of. Remember, specific heat. The specific heat of a substance is a characteristic property of that substance, and it does not depend on the amount of the substance. The larger the specific heat of a substance, the more energy must be added to raise the temperature of the given amount of that substance, and the more heat a given amount of that substance can store. So in other words, if you have a big specific heat like water does, it takes a lot more energy to raise the temperature of water. You know that. You know it takes a long time to boil water. In general, metals have fairly low specific heat. Water has a relatively high specific heat. And I guess I want to go back and comment on this one about how it doesn't depend on the amount of the substance, because the definition says 1 gram, 1 degree Celsius. Okay? Well, it doesn't matter if you have a cup of water or a gallon of water. Water always has a high specific heat. The specific heat is always around 4. Okay? Tip: remember that heat cannot be created or destroyed. Therefore, in a closed system, any heat lost by one object or substance must be gained by another object or substance. So the negative Q, which is lost, equals the Q, which is gained. All right, example 1. Calculate the initial temperature of a substance. A student dropped a 25-gram cylinder of aluminum into a foam cup containing 100 grams of water at 25 degrees Celsius. The final temperature of the water and aluminum was 28 degrees Celsius. What was the initial temperature of the aluminum cylinder? The specific heat of aluminum is 0.90 joules per gram degree Celsius. The specific heat of water is 4.186 joules per gram degree Celsius. Okay, first of all, was the aluminum hotter or colder than the water? The water started out at 25. The water ended up at 28. That tells you that your answer for aluminum better be higher than 28. All right, let's collect and strategize. First, calculate the amount of heat the water gained. Then, use that information to determine the initial temperature of the aluminum must have had. The following information is given. So as always, we make a list of what we know. The temperature change of water equals 28 degrees Celsius minus 25 degrees Celsius. So our delta T, or change in temperature, is 3 degrees Celsius. Mass of aluminum is 25 grams. Mass of water is 100 grams. The equation relating heat, Q, specific heat, C, mass, M, and temperature change, delta T, is Q equals MC delta T. First, calculate the heat gained by the water. Okay, so the mass of the water was 100. The specific heat of water is 4.18. The change in temperature is 3. Multiply it together, we get 1.3 times 10 to the third, or 1,300 joules. Then we're going to keep going. The water gained 1.3 times 10 to the third joules of energy. So the aluminum must have lost the same amount of energy. Remember, the energy going in equals the energy going out. So if the water gained 1.3 times 10 to the third joules of energy, that's how much the aluminum had to lose. Now, solve the specific heat equation for delta T. Remember that because the aluminum lost heat, the value for Q in the equation must be negative. All right, so we used our algebra to rearrange the problem. So it was Q equals MC delta T, and they put these little ALs here to remind us that, oh, now we're doing the heat of the aluminum, the mass of the aluminum, the specific heat of the aluminum, the change in temperature of the aluminum. So they changed the subscripts to make it a little easier. All right, so we use our algebra skills to rearrange it. So delta T equals Q over MC. Our change in heat has to be negative because the water gained it, the aluminum lost it, so it's got to be negative. The mass of the aluminum was 25 grams. The specific heat of aluminum is 0.9. Put it in your calculator, you get negative 58 degrees Celsius. Okay? The aluminum's temperature was decreased by 58 degrees Celsius. That's what that negative means. So its initial temperature must have been 28 degrees Celsius, because that's the temperature it ended up, plus 58 degrees Celsius. So why are we adding when it was negative? Because it decreased by 58, so we're doing the opposite. We're saying, okay, well, what did it start with? So it ended at 28 plus 58 more degrees. The aluminum had to start at 86 degrees Celsius. As always, if you have questions about the problems that we're doing, please come to office hours and see me. Example 2, determine the specific heat for a substance. When a 10-gram cube of an unknown metal gains 25 joules of heat, the temperature of the metal increases by 5.57 degrees Celsius. What is the identity of the metal? Solution, collect and strategize. Use the equation relating heat, specific heat, mass, and temperature. Change to calculate the specific heat of the substance. So in other words, use your algebra skills and rearrange it. Then compare the specific heat with the values in the table of specific heats shown to the right. The information is given in the problem. So the mass of the metal is 10 degrees. Heat gained, 25 joules. Temperature change, 5.57 degrees Celsius. Hit the pause button, see if you can figure out the first part of the answer. And then here is the table that you're going to compare it to. If you're doing it yourself, go ahead and hit pause. Otherwise, we'll come back to that. Solve. First, solve the equation for C, the specific heat in the metal. So Q equals mc delta T. Use your algebra skills. C equals Q m delta T. Go ahead and try it yourself if you haven't. Throw in your numbers, 25 joules divided by 10 times 5.57 degrees Celsius gives us an answer of 0.449 joules per gram degree Celsius. So 0.449. 0.449. Which one of these is close to 0.449? The closest one is iron. No, it's not exactly, but it's close. It's the closest, and in labs we sometimes have slight experimental error. All right, so compare this value to those in the table. Only iron has specific heat near this value. Therefore, the metal must be iron. All right, we got to do problems 1 and 2. Number 1, a student drops 15.2 grams sphere of copper into a beaker containing 150 grams of water. The initial temperature of the water is 23 degrees Celsius. The final temperature of the water and copper is 23.6 degrees Celsius. If the container is perfectly insulated, how much heat in joules does the copper lose? Okay, so hit the pause button, figure it out yourself. So you should make a list of everything: the mass of the copper, the mass of the water. What are you going to write down for delta T? Well, you got to have a change in temperature. So delta T is 0.6. And I'll go ahead and go through the answer now. So the amount of heat lost by copper is equal to the amount of heat gained by the water. Because remember, we can't magically create or destroy heat or energy or mass. So the amount of heat gained by the water has to equal the amount of heat lost by the copper. The change in temperature of the water is 23.6 minus 23, or 0.6 degrees Celsius. Substitute this value in the heat equation for Q. So our mass is 150. We know the specific heat of water is 4.18 joules per grams degree Celsius. Our change in temperature is 0.6 degrees Celsius. Our answer is 3.76 times 10 to the 2, or in other words, 376 joules. Therefore, the copper lost 376 joules. So in this problem, they're assuming that you remembered the specific heat of water as 4.18 joules per gram degree Celsius. All right, question number 2. A scientist adds 46.3 joules of heat to a 13.4 gram sample of an unknown substance. The temperature increases by 1.4 degrees Celsius. What is the specific heat of the substance? From the table on this page, determine what the substance is. Okay, so if doing it by yourself, hit pause, and then I'm going to scroll up here so that you can see the table. So you can hit pause again and find your final answer in the table. And now I'm going to go over the answer. So we're solving for specific heat. Rearrange your algebra problem. plug in your numbers,